Swayam Prabha. Digital India. Educated India.
The divergence of the electric field is equals to the charge density over the permittivity. What we got as a physical interpretation from that is that if there is an enclosure having certain charges with a charge density of rho, then the net electric field outflux is equals to the charge density over epsilon naught. Okay. We will move on to the concepts of electrodynamics now. Electrostatics we have talked about where charges were at rest and they were not moving. Now, in electrodynamics the charges are moving, and what is a moving charge? A moving charge is a current, right. So, we will talk about currents and electromotive force and Ohm's law. We will start with electromotive force. And Ohm's law. Okay. The EMF or the electromotive force we will revisit again when we will talk about magnetism. This is more from a electrical perspective rather than a magnetism perspective. We will introduce magnetism into the concepts as we proceed. Okay. So, to make a current flow, the charges needs to be pushed. Okay. So, if there are charges in a conductor, say this is a conductor, then the charges needs to be pushed through this conductor for the charges to flow and a current to happen. Okay. The current density is given by the J vector is proportional to this force. Which is acting on the charges. Let us say the force is an F vector. So, there is a relation which shows us direct proportionality between the forcing term, this is your forcing term, current density rather, and the proportionality constant is called the electrical conductivity of the material. With the unit, it is inverse of the resistivity. So, if the resistivity has a unit of ohm meter, then this will be Siemens per meter, right. Siemens is 1 by ohms. Okay. So, this is electrical resistivity. The relation between conductivity and resistivity is sigma is equals to 1 by rho, where rho is the resistivity. All right. Now, this force that is driving the charges through, it can be any kind of force. Nature does not care what kind of forces are acting to move the charges or that causing a current, right. It can be, for the sense, it can be gravity, it can be an electric force, it can be a chemical force, it can be anything that is pushing the electrons through. Now, electrons does have a natural behavior and a tendency to move under the influence of an electric and magnetic field. Right. So, all the forces can be anything for our sake of understanding and for our sake of modeling electromagnetic system, we consider electrical forces and magnetic forces. Therefore, we can replace this F vector by the Lorentz force, per unit charge that is your F vector is E vector plus V cross B vector. Therefore, our J is equals to sigma into V cross B. Okay. Now, if the electrons are moving at a very slow speed through a conducting material, the terminal velocities of electron can be as slow as 10 to the power of minus 4 meter per second. These are very slow velocities. In that case, we can ignore this magnetic field effect, and we can assume that for slow moving electrons or small velocity of charges, our J vector is equals to sigma into E vector. This is our Ohm's law. It is the initial or a fundamental definition of Ohm's law that the current density is equals to the electrical conductivity times the electric field vector. All right. Something that is more popular or a popular version of Ohm's law is that V is equals to IR. Okay, this is a more popular version, much rather used, but if we look at from a vectorial perspective, or we consider these as tensors and vectors, then J is equals to sigma into E. Okay, well, and the conductivity is a tensor. It changes the so we can write this as a tensor. It's a tensor which transforms the electric field to the current density. Now, let us take a divergence of both sides. So, if we take divergence on both sides, then we can have sigma del dot E is equals to del dot J, or del dot E is equals to 1 by sigma del dot J. Now, for a steady current, del dot J is equals to 0. So, del dot E is also equals to 0 for a steady current, right. Now, we know that del dot E is equals to rho over epsilon naught. So, that means that in a conductor with a steady current, the charges are balanced out and it is electroneutral, which indicates electroneutrality. Of the conductor. If del dot J is not equals to 0, or if this del dot J is equals to sigma into rho over epsilon naught, considering our Gauss law for electrostatics, then that means that the charges are not uniformly distributed. Some domains have a larger magnitude of positive charge, some domains have a larger magnitude of negative charge. So, we are looking at one domain which has a larger positive charge, that will give you a positive gradient of your current density, and or sorry, a positive divergence of your current density, and a negative set of charges will give you a negative divergence of the current density. Right. So, these are related. However, to maintain electroneutrality of a conductor, that means that the positive charges and negative charges balance out. This del dot E should be equals to 0. And let us take a look at the concept of the electromotive force. So, the electromotive force is that the current, let us answer the current is same everywhere in a conducting material. Right. So, let us take a system. We have a resistor and we have connected it to a battery. Right. So, this battery is what is creating a potential difference that is causing the current to flow through this conductor and through this resistor. Okay. Now, if we consider that there is an accumulation of charges, then an electric field is generated. To neutralize the charge accumulation. Right, this makes sense, right. So, we have seen del dot E is equals to 1 by sigma del dot J. In case that there is charge accumulation, which is equals to rho over epsilon naught, there is some charge that is present, it will generate an electric field, a gradient or a divergence of electric field, and that will cause the charges to disperse and become electroneutral. So, so this is the nature's way to create a state in which the system is electrically neutral. Now, for the charges to flow through this loop or through this circuit, there needs to be some force. So, there are two real forces which drive the current. Okay. So, the first is called the source force, Fs, which is confined in a small area or a small domain of the loop or the circuit, typically a battery. Right. So, your battery itself will be having some potential difference that is driving the circuit, and this force within the battery itself, it is Fs, that is your source force, and the second force is your electrostatic force, E, which communicates the influence of the source force Fs to distant part of the circuit. Okay. So, in this loop we have the source force that is originated by the battery or the circuit, and then there is resistor that is far away. How will the resistor know whether the battery's voltage has changed or whether we have switched on or connected the battery or disconnected the battery? How would it know? So, and the battery needs to communicate this information to the resistor, and that is where the electric field comes in. So, the electric field will go up to the resistor and will communicate, or it will tell the resistor that the battery has been connected and there is now current going to flow through the system. Right. And this communication typically happens by the speed of light in the dielectric medium. Okay. So, our net force is equals to Fs plus E, and we can write it in vectors. These are all vectors. Okay. So, where Fs, it can be any kind of force, it can be a chemical force from a battery, it can be piezoelectric, it can be photoelectric, it can be anything else, it can be a capacitor storing charge, etc. So, it can be any kind of force or any kind of device which on stimulus can generate a potential difference, allowing the charges to flow across the circuit. All right. And then the effect of this force is determined by the electromotive force. E is equals to integral over the loop that we have shown in the last slide, this loop over this loop of circuit of our force Fs dot with dl, right, and which is also equals to integral of F dot dl. Now, F is equals to Fs because integral over a closed loop for an electrostatic system is equals to 0, or del cross E is equals to 0 for an electrostatic system. Okay. So, here E is our electromotive force or our EMF for the circuit. Now, an ideal EMF is where there is no internal resistance at the source, the net effect of the force, or the net force on the charges is 0. Okay. So, if there is no internal resistance, that means that we have a superconducting material, then our conductivity is infinity or resistivity is 0. Right. In that case, we have seen that the net current that will flow will become infinite, right, immediately, and therefore, there is no actual force or nothing to resist against that motion. There is no R, and therefore, for an ideal EMF, the net force acting on the charges is 0. So, the charges can flow freely. There is no forces acting on it. Okay. So, if such is the case, then F is equals to 0 and E is equals to minus F s. Okay. From here we can say that the voltage of the battery, the potential difference between 2 points A and B is equals to integration of A into B E dot dl. This is what was our definition for our potential difference. If you go back to the last lecture, you will be able to find the potential difference derivation, and this is equals to minus of F s. Therefore, it is integration from A to B of F s into dl dot with dl. And if we see the derivation for integration of F s dl over a looped value, then we can say that over a loop as well, this is applicable, and is equals to electromotive force. So, our voltage is the same as the electromotive force for our given circuit. Okay. Now, F s, or the source force, it is 0 outside the battery. Of course, that is a source force. So, the force is exerted by the battery. Any place outside the battery, that force needs to be carried by a field, that is your electric field. What is the battery's work? So, the battery's work is to provide a voltage difference or a potential difference equal to the electromotive force. Okay. And the resultant electrostatic field that is developed will drive the current. Current in the circuit. Make sense? Yes? All right. Then we will talk about motional EMF. And now, so far we have had a battery which was creating a potential difference that was causing the currents to flow. We have seen that for that the battery is resistanceless. That means that the net force is 0. From there we found out that the voltage was equal to the electromotive force. Now, consider the force due to a moving current source through a magnetic field. Okay. So, assume that there is a magnetic field in a domain. Say this is our domain for our magnetic field. Magnetic field is in plane of this. This is your B vector. Consider that this is our loop for our circuit. Let us mark this point A, B, C and D. Say this distance is x, this height is h, and this resistance is R. Okay. So, this is our configuration. We have a loop which is partially covering the magnetic field, and what we are doing is we are pulling the loop to the right with a velocity v. Right. So, we are dragging it. Now, what will happen on the action of dragging? It will induce a current due to the forces on the charged particle that will cause the charged particles to rotate in a clockwise direction. So, if you pull this on the right, you will induce a current in the clockwise direction. This is an example of a primitive generator. Right. So, this is our shaded region. We have this loop which is being dragged to the right. Now, the forces on the charge. So, if you look at this segment of the, so consider this segment of the conductor AB. Okay. The forces or the magnetic force on the charged particle. So, B is in this direction or in the downward direction in plane, you are pulling it to the right. Right. So, you have a V cross B, then using your right hand thumbs rule, your velocity is this way and you are curling this way. So, your force is in the upward direction. Right. So, on the charged particle is upwards, and equals to Q into V into B, right, and the direction is perpendicular to both V and B, and that is a cross product of V cross B. So, this is your force that is acting on the particles in the loop. This will create or this will induce a clockwise current. Okay. So, the force that is pulling and the charges up is what is causing this induction of current through the coil, right. So, say that the charged particles are moving in AB upwards with a velocity of u. So, your F pull will be equals to u into B, that is your force to pull through the magnetic field is u into B in the upward direction. And what we will get is that the resultant direction, that is now your this is your particles is moving in the u direction, your system is moving in the v direction, the resultant is in the w direction. Again this segment has a length of x and height of h. So, you are moving in a direction that is theta, that is h over cos theta. So, integration of F pull dot dl, and what is this quantity? This quantity is the work done per unit charge, will be equals to u into B. What is the distance it has travelled? It is h over cos theta, and the dot product will give you the sin theta. So, you will have u into B into h into tan theta, and u tan theta is equals to V. So, that is then V B into h, and this is the force or this is the pull that is being generated on the body or on the particle, right, the VBH. This is our induced EMF in the body. So, the induced EMF formula, therefore, E is equals to integration of over the loop of our magnetic force dotted with dl, and that is equals to V into B into h. This induced EMF will drive the current through the body. Okay. Now, let us take a look at what is a magnetic flux. So, the magnetic flux due to this B vector is similar to electric flux. So, B is the magnetic field strength, just like we have the electric field strength. Our electric flux was integration of the field strength over a given area. Right. So, in the same way, phi B is equals to integration of B vector dot n cap into ds over a given surface. So, we have a surface, how much is a magnetic field lines flowing through it, that is your magnetic flux. In this case, this is equals to b into h into x for our case. So, if you look again, if you go back a few slides, we can see that the area is h into x and your field is b. So, b into h into x. Now, as the loop moves, the flux reduces and therefore, d phi b by dt is equals to b into h into dx by dt, which is equals to minus b h into v, and this is our minus into epsilon, right. This is clear. It is reducing, that is why the negative sign, it is going the velocity is in the right hand direction, and therefore, it is equals to minus epsilon. So, our electromotive force equals to minus of d phi b by dt. Okay. This is the flux rule of EMF. Okay. We also know that E is equals to integration of EDL from our last case study. From a few slides earlier, we have seen that our induced EMF we can find out based upon over here E is equals to integration of EDL minus integration of EDL. Okay. So, we now have an understanding of what an electromotive force is. It can be induced by some chemical source like a battery or something else. It can also be induced due to a time varying magnetic field. Now, electromagnetic induction and Faraday's law. So, our former experiment was done by Faraday, in which he had 3 experiments done. So, he took the same situation of R and he did 3 experiments. In the first experiment, he pulled the loop with a velocity v, was pulled with a velocity v to the right. Second was that this magnetic field source B was pulled to the left, B plane was pulled to the left with a velocity v, and the third case B was time varied. What you observed is in all of these 3, whether you are keeping the magnetic plane fixed and you are pulling the loop, whether you are keeping the loop fixed and pulling the magnetic plane, whether you are keeping both fixed and you are time varying the magnetic field, in all of them you are inducing a current or you observed that there was a current being induced within the loop. Okay, this was his observation. So, with that let us write down our formula. E is equals to minus d phi b by dt. So, a changing magnetic field induces an electric field. This was his law, and this is the basis of the Faraday's law of induction. Okay. So, epsilon is equals to integration over EDL equals to minus d phi b by dt. I wrote a sign wrong, this should be plus. So, d phi b by dt. Now, the magnetic flux phi b, we can replace this phi b is equals to integration over a given surface of b vector dot n cap s into ds. We can substitute this, therefore, integration over EDL over a loop which is binding a surface is equals to minus d by dt of integral over the surface of the magnetic field dot with n cap into ds, which is equals to minus integral over surface del b by del t dotted with surface normal into ds. This is our Faraday's law, the integral form of the Faraday's law. The differential form for this, you can convert this using Stokes theorem. So, using Stokes theorem, our integration over a loop del s, we had E dot dl would be equals to integration over surface del cross E dot with the surface normal into ds. Therefore, integration over surface del cross E is equals to integration of surface minus del B by del T dot with surface normal into ds. So, we can remove the integrations from both sides, and del cross E therefore equals to minus del B vector by del T, and this is our Faraday's law, the Faraday's law of induction. We are inducing an electric field due to a time varying magnetic field. So, if the magnetic field strength is varying by time in any way, whether due to the motion of a loop, whether due to the motion of a plane, or whether due to some electromagnet which can induce a time varying magnetic field, our electric field will be induced, and that will create the current to flow through the given loop. Okay. So, what we can conclude from this is that there are two kinds of electric fields. The first one is our normal electrostatic field, due to static charges. So, we have a potential difference, and that potential difference is causing the current to flow. And a second one is an induced, magnetically induced field, due to changing magnetic flux or changing the time varying field. So, we can say that there are two kinds of EMFs. Actually, the second one has a different name, it is also called MMF, magnetomotive force. First is called electromotive force, but you can count them together. Their influence is the same. It is a potential difference that causes the charges to flow and induces the current. One is due to some chemical change or due to a potential difference from an electric source. That electric source can be mechanically induced, chemically induced, can be photoelectrically induced in any way. The second one is the induction of electric field due to a time varying magnetic field. So, these two, and the second one is the basis of all electric generators. As you would rotate your coil through a magnetic field, since the coil is moving through the magnetic field, it will induce an EMF, and that EMF can be used to generate current or to generate electricity. Okay. Then we will go on to our next topic, that is your magnetostatics. So far what we have covered is are our electrostatics and our electrodynamics. So, charges which are stationary, which are not moving, or the charges that we are moving. Why would the charges move is because of an electric field or electric potential that is causing the charges to move or charges to flow. We have also seen that how magnetic fields can generate electric fields. Now, we will talk about magnetostatics. What are these magnetic fields? Right. So, we have been using magnetic fields so far just by the term itself. Now, we should know magnetic fields can be induced by some current that is flowing through a loop. It can be induced due to polarity of certain materials. We have seen permanent magnets, we have seen electromagnets. These are the two kinds of magnets that are present. Permanent magnets, our atoms have neutrons and electrons and protons. So, the nucleons, that is a neutron and proton, they are rotating on their spinning about an axis. Likewise, electrons are spinning. The spin of the electrons and the spin of the nucleus both induce magnetic fields. Now, if they are aligned and all the atoms are aligned in a certain way, then that induces magnetic fields of materials, and that is why you have permanent magnets like neodymium iron boron or ferrite magnets, the horseshoe magnets that you use, or the bar magnets. They are due to that all the atoms are arranged in a certain way, that the spin of the electrons and the spin of the nucleus both are charged particles, right. Electrons is negatively charged, ions is positively charged. So, moving charged particles induces current, and that current induces magnetic field. Likewise, if I have a conductor like this through which current is flowing, then there will be induced magnetic field around it due to the movement of the charged particles. All right. So, with this understanding, we can start our magnetostatics. So, a charge under motion induces a magnetic field in its vicinity. Okay. So, just like we had a changing magnetic field induce an electric field, a moving current due to an electric field would also induce a magnetic field. Okay. Look at magnetic forces. So, magnetic forces, this comes from Lorentz law. So, your F vector is equals to for the magnetic component is equals to the charge times V cross P, right. So, if a charge is moving with a velocity V through a magnetic field, then the cross product of the velocity vector to the field vector times the charged quantity or the magnitude of charge gives us the magnetic force. If an electric force also exists or electric field also exists, then the total force will be equals to Q times E vector plus V cross B vector. So, we have an electrically induced field F E and we have a magnetically induced field F mag. All right. So, what we will find out is that magnetic forces do not do work or do not contribute to work. Okay. Let us see if we can validate this hypothesis. So, say consider a charge moving a distance dl, which is equals to the V dt through a magnetic field B. Then the work done due to the magnetic component of the charge is equals to F mag dot with dl. Right. What is our magnetic force? It is V cross B into Q dot with the V vector into dt. Now, we can see that V cross B is perpendicular to both V and B into a dot product with the V vector itself will be 0. So, this comes out to be 0. Therefore, magnetic forces do not do work or do not accelerate or deaccelerate a charged particle, it can only change directions. So, the effect of a magnetic field to a charge is that if a charge is moving through a magnetic field, it will start rotating or start spiraling. However, it will not induce any acceleration or deacceleration to the particle. Okay, that is a very important statement to make. Whenever you would do modeling using magnetic fields, so you are doing magnetohydrodynamics, you should have a sense or an understanding of how these charged particles would behave under the magnetic field. Okay, now let us look at what is a current and what is a continuity equation. So, we have already considered in electrodynamics what a current is. So, a current may arise or may be defined as charge flowing through a conductor per unit time. Okay. So, if you have some conductor which is through which some charge density lambda, which is varied over the length, is flowing with a velocity v. Let us consider a segment which is passing through a point P, which is v dt. So, this charge, this lambda charge will flow through this segment over P having a length of v vector into dt. So, our current can be defined as I vector is equals to lambda times v vector, where lambda is the charge density, is a linear charge density, and v is the velocity of the particles or the charged particles in the conductor. Okay. Now, it can be that typically in a conductor the ions, the positive ions are in the lattice and the electrons are free to move in the conduction band and they can move freely, then this formula is applicable. But in certain situations, unusual in certain unusual situation, for example, in a electrolyte, right, say for a battery. in which you have the flow of both positive ions and negative ions. In that case, this equation will be modified as lambda plus V plus lambda minus V minus. Okay, so only in the case of some unusual situation in which you have both positive and negative ions which are free to move, then we need to add the contribution from both the ions to the total current. Okay. The magnetic force on a segment, this segment V dt, will be equals to integration of V cross B vector into dq, which is equals to V cross B vector into lambda dl. Okay. So, over this lambda dl is what we are finding out how much charge is there, and this charge effect due to the velocity v and a magnetic field or a magnetic field that is being induced. B vector is a magnetic field, is equals to this. Now, if we take this lambda and we multiply it inside with this, we can find out equals to I vector cross with B vector into dl. Okay. Our magnetic force is therefore the current cross product with the magnetic field strength integrated over the segment of our conductor. That is how you find out the magnetic force. Okay. We can take an example, a simple example, say that this is a domain of some magnetic field B, and we have a conductive loop of width A, and that is being pulled down to some weight mg. We have a force against it. This force equals to I cross B into dl. Say I is the current, B and into dl is the length of the conductor, that is A. So, we can find out what is the current that will flow to counter or balance the forces. In this case, I will be equals to mg over B A. Okay. So, if this much current is flowing through the conductor, then the gravitational force is countered by the magnetic force, and the loop is hanging or suspended in air. Okay. Now, let us find out what is the current per unit area, that is our current density. Is J, and we can define J is rho into V vector, where rho is the volumetric charge density and V is the velocity of the charged particles. So, that is our you can check the units, right. It is coulomb per meter cube into meter per second, that gives you coulomb per meter square second or amperes per meter square. The unit is consistent. Always check for units for whatever equation you are writing. Therefore, the current can mention as I is equals to integration over a given surface of a loop of j vector dot n cap into ds, which you can convert by the Gauss divergence theorem into volumetric differential of del dot j into dv. Okay. Now, if we can substitute our rho into this and by charge conservation, we can also say that I is equals to minus integral of del rho by del t into dv. Okay. The negative sign is due to the flowing of electrons is in the opposite direction to the flow of current. So, current we always take as a positive ion transfer from positive to negative. Electrons will always flow from negative to positive, right. So, with that we put a negative sign over here. Okay, if we equate both the equations, and this is V. So, equating the two, what we get is del dot j is therefore equals to minus del rho by del t. This is called the continuity equation of electromagnetism. This is not the continuity equation for your fluid mechanics, please do not confuse with that. This is for electromagnetism, and it says that the divergence of the current density is equals to minus del rho by del t, that is the time derivative or the partial time derivative of the charge density. Okay. Now, we have an understanding that that the current flowing through a conductor is causing the charges to flow, and the charges flowing through it is inducing an effect, a resulting magnetic field. Now, if you impose another magnetic field on top, then we can see that the flow of the charged particles in the presence of that magnetic field will induce a magnetic force. Okay. Now, we have the Biot-Savart's law. So, the magnetic field through a straight line can be written as a formula very similar to the Coulomb's law. B vector equals to r vector mu naught by 4 pi Okay. So, this is our magnetic field strength. If we have a steady line current, it can be any loop, in a twisted loop or a circular loop or a straight wire. It is equals to mu naught by 4 pi, where mu naught is the permeability of free space or absolute permeability, and is equals to 4 pi 10 to the power of minus 7 of newtons per ampere square. The output of this equation will give you the units is Tesla, and the Tesla is equals to 1 in SI unit is Newton per ampere meter. Okay. So, what is this? Say this is a loop through which some current is flowing, that is your current I. We take a small segment, that is dl, and we take a point which is separated by a distance of r vector from this dl. Then what is the magnetic field induced at that point due to this current carrying loop for this small segment dl, and therefore, if you integrate over the entire loop, what will be the net magnetic field at that r location, or as a function of r, is this Biot-Savart's law. That is the definition of the Biot-Savart's law. Now, if you are looking at the divergence and curl of B, so what we are considering, we will talk about Ampere's law. So, from Ampere's law, let us consider the B vector for an infinite straight line wire. Okay. What we are doing, we are taking an integration of B that we are calculated from the Biot-Savart's law into dl, and that is equals to integration of mu naught into I over 2 pi s into dl. What I did is this is our straight wire. Our magnetic fields are in concentric circles. We are taking any one of the loop, radius of s, and we are trying to integrate this magnetic field throughout this loop. So, this integration of mu naught I over 2 pi s dl will be the value. Okay. Now, these are constants will come out. So, you will have mu naught I over 2 pi s and integration over dl. This will be integration will be from 0 to 2 pi, that is one circle 0 to 2 pi. This 2 pi s will cancel out, and you will have mu naught of I. If there are a bunch of wires in this case, then you can say that mu naught into I enclosed by that loop or by that hypothetical domain of radius s. So, if you have a hypothetical domain of radius s. All right. Now, I enclosure is equals to integration of j dot n cap ds, this we know very well, over the given surface S. So, if we compare the two, we can say that integration of B dl is equals to mu naught times integration of j dot n cap into ds. This is our Ampere's law. Okay. We can modify this Ampere's law by using Stokes' theorem, and we can say that by Stokes theorem integration of B dl is equals to over this length L is equals to del cross B dot with the surface normal into ds, and if we compare both of them we will find out that del cross B is equals to mu naught into J. This is our Ampere's law. Our Gauss's law we can find out by taking the divergence of the B vector. The divergence of the B vector is equals to mu naught over 4 pi integration of del dot J cross del R over R square into dVc. Okay. Now, our divergence say this is our body, our J is flowing through this is our coordinate system x prime, y prime, z prime, and we are finding at a location of x, y, z, and that is where our B is calculated, and the difference between the two x I minus x I prime is our R vector. So, divergence of this we can take del R by R square separate and del dot of this. So, this will be okay. The first term is 0 because J is from a different coordinate system and the cross product of the two will tend to be 0. The second one is also 0 because R is in the direction of the gradient and the cross product again will be 0. So, since both of the terms are 0, therefore, divergence of B is equals to 0, and this is our Gauss's law for magnetism. Finally, what Maxwell did was he showed that Ampere's law had a flaw. So, the flaw in the Ampere's law was that if we look at the Faraday's law, then del cross E was equals to minus del B by del T. If we take a divergence on both sides, so both sides is equals to 0, del dot del cross is 0 and divergence of B is 0 from the Gauss law. If we do the same with the Ampere's law, then it does not work. Del cross B is equals to mu naught times J. So, del dot del cross B should be equals to mu naught times del dot J. Now, this term is 0, but this term can actually be minus del rho by del T. That is what we have seen, that some current can exist. If it is a steady current, then that term is 0, that is fine. If for an electrostatic case that we have seen in the case of electrodynamics. But if it is not a steady current, then del dot J is equals to del rho by del T from the continuity equation. Okay, then what can be done is that del dot J, which is equals to minus del rho by del T, we can replace rho from our Gauss law, that is epsilon naught del dot E. Okay. And we take epsilon naught out and we will have del by del T of del dot E is equals to minus epsilon naught of the divergence of del E by del T. We can remove divergence from both sides, and this current is called the drift current, and the drift current is equals to minus epsilon naught into del E by del T. So, there is this additional current drift or displacement current rather. This term can be added to our original Ampere's law, and the Ampere's law can be modified. So, modified form of the Ampere's law would be therefore, so we can modify this del cross B and add up this extra JD. So, del cross B therefore will be equals to mu naught of J plus this JD, which is equals to mu naught of J plus epsilon naught mu naught of del E by del T. This is our Maxwell Ampere's law. Now, this law it is modified that if the system is not having a steady current in which del dot J is not 0 and equals to minus del rho by del T from a continuity equation, then we can then we have this additional current, that is our displacement current, that is working. Now, finally, let us take a look at our wave equation and how a wave equation can be determined. So, our Maxwell's equation For free space, that is for vacuum, is del dot E is equals to 0. There is no charge in vacuum. Del dot B is equals to 0. Right, again del dot B is 0 from Gauss law of magnetism. Then del cross E is equals to minus del B by del T, that would be there, and del cross B is equals to mu naught times J is 0 and the JD is there, that is epsilon naught del E by del T. So, there is no current, there is no charge in vacuum, therefore, rho is 0, J is 0. However, this displacement current does exist, epsilon naught del E by del T. Let us put in the vector sign. Okay. Now, let us take this del cross E is equals to minus del B by del T, take curl on both sides, minus del by del T of del cross B. Now, this can be expanded by the triple product rule, and that is the gradient of del dot E minus del square E equals to minus del by del T of mu naught epsilon naught del E by del T. The first term is 0 from this first equation. The second term, therefore, it gives you del square E is equals to mu naught epsilon naught del square E by del T square. This is a wave equation, right. This wave equation you can rewrite as del square E by del T square is equals to c square of the Laplacian of E vector, where the p is the speed of sound in free space, and that is equals to 310 to the power of 8 meter per second. A similar equation you could derive if you start with del cross B and do the same treatment, and you will find out that del square B would also be equals to mu naught epsilon naught times del square B by del T square. So, with that we have finished up the concepts of electromagnetism. These wave equations you could derive very similar to how you have solved for Navier's equation. For a wave we have solved for the transient Navier's equation as well in solid mechanics. So, wave equations you can try to derive using the same concepts, and in the next class we will take up electrochemistry. So, thank you for listening today.
Hello and welcome to this piece of literary snippet. Perhaps the most popular literary genre after novel is the short story. Sharp, compact narratives whose charm lies not only in what is said, but also in what remains unsaid. Today I will be reading one of the shortest instances of a short story that I have ever encountered, and indeed, the very charm of this particular story that I am going to read out today lies in the way it abruptly ends. It is an ancient tale from Mesopotamia which has been retold by several authors, among whom the name of Somerset Maugham stands out. The adaptation that I will be reading out is perhaps the closest to the one that Maugham wrote. The story is titled in all of its adaptations almost as Appointment in Samara. Here is the story. A merchant in Baghdad once sent one of his servants to the market. The servant was supposed to buy provisions for the merchant, but when he returned, he came back empty-handed. Indeed, the servant had all gone white, and trembling with fear, he told his master that he had met death in the marketplace. When I entered the market, the servant said to his master, I was jostled by a woman, and when I turned to look at her, I saw that she was death. I am very scared, master, because death looked at me with a threatening gesture. can you please lend me your horse so that I can fly away from Baghdad to the town of Samarra and thereby escape death?" The master, being a good man, gave his servant his best horse and saw him gallop off to Samarra to escape death. Then the master himself went to the marketplace and confronted death. "Why did you make a threatening gesture to my servant?" asked the master to death. And death replied, "It was not a threatening gesture. Rather, it was a start of surprise. I was astonished to see your servant here today, because this evening I have an appointment with him in Samarra." See you in the next episode of Literary Snippet.